Well, hello and welcome. In this video, I'll be covering section 5.5, which is over solving exponential equations as well as logarithmic equations. My goal for you by the end of the video is to be able to solve those two types of equations, both exponential and logarithmic. So we'll go ahead and start with talking about some of the properties that we'll be allowed to use when it comes to solving these exponential or logarithmic equations. To start it off, we'll talk about the base exponent property, which is essentially, if I were to try and simplify this, it's basically if you have an exponential on both sides of an equal sign and they both have the same base, then whatever the powers are would have to be equal if the two exponential parts were actually equal. So notice basically you can kind of just drop whatever the base is. So notice base of b on both sides, and then my exponent of x and y can basically just turn into a statement where I can ignore the bases and just say that the two exponents should equal each other. Another one that's very similar with logarithms is if you have two logarithms on both sides, notice in this case they both have the same base. If they're truly equal to one another, then the inside parts would have to be equal. So it's basically another way that we could just eliminate or drop whatever the logarithms are from both sides. And then another thing that we've already covered that we can always use when it comes to solving exponential or logarithmic equations is the ability to convert forwards and backwards from exponential form into logarithmic form and vice versa. Now with regard to solving equations, even those that involve exponentials or logarithms, every single problem can kind of have its own unique twist or thing that needs to be done. So ultimately, I'll just kind of talk about some of the strategies to try, first with exponentials and then with logarithms, such that hopefully by just trying some of these things, you would then be able to kind of get the ball rolling in how you could solve or isolate the x. So one possible thing to try is to take advantage of that base exponent property I just presented and attempt to just basically write each side of the equation with an exponential that will have the same base, because as soon as you can make it such that both sides have the same base, then it should just be the two exponents would need to equal each other. Another option you could try if you aren't able to make both sides have the same base is to just isolate whatever the exponential is. So if you notice there was only one exponential, at that point, once you have it isolated, you should then be able to convert to a logarithm and potentially solve for whatever variable you end up having. So more than likely, if it's an exponential equation, the variable you're trying to solve for is up in the exponent area. So by converting into a logarithm, it would then get that, I guess, either statement or expression out by itself or out in the open, such that now you actually can do some extra steps to try and get whatever the variable is isolated. Then another option is if you have exponentials on both sides but you can't make the bases match, then what we could do is just introduce a logarithm to both sides. The two that make the most sense, just because these buttons exist on your calculator, would be either the common log or log base 10, or the natural log or the log base e. And once we have a logarithm on both sides, that then should allow me, by utilizing the power rule, to move any exponents out in front or as coefficients of those logarithms. That should then open up the ability to kind of go through and potentially, again, isolate whatever variable they're wanting you to solve for. As far as some strategies for logarithms or logarithmic equations, one option you can always try and do is, if you have multiple logarithms, try and find a way to combine them utilizing some of the rules that we explored last section, such as the product rule or the quotient rule, or even if you notice that you can move maybe some coefficients up as exponents. At that point in time, maybe that would get the ball rolling towards being able to solve for whatever variable you have. So again, this is something we would always look to see if we can do on both sides of the equal sign. So if you notice that there's multiple logs both on the left and on the right, then ultimately if we can try and get it to where it's just a single logarithm on both sides, that should, in theory, make things a little bit easier to try and go through and solve. And in the event that we could do that, what we could also try is to attempt using the property of logarithmic equality that I mentioned earlier, where if both sides have a logarithm with the same base and they're set equal to each other, then the inside portions of those logarithms should also have to be equal to each other. So we would just set those two equal and actually get rid of or eliminate our logarithms from our equation. And then another option with logarithms is to try and convert from log form into exponential form, which then again would open up the ability to, if your variable was inside of a logarithm, which is more than likely what will happen, then you would have it out in the open such that now you could try doing some steps to try and isolate. So everything from here on is basically going to be me working through some of these strategies and just solving some of these types of problems. And I'll try and verbalize what my thought process is for each of, I guess, the problems, or what my approach is, I guess, for each of the problems to be able to actually go through and solve them. So this first example we'll start with is an exponential equation. So again, notice it just wants us to solve, so the only variable I see is an x, so we're just trying to get x by itself. With it being up in the exponent area, it does make things a little trickier, so what I know I can do is some of the strategies that I presented earlier. This particular one, if we look at what 32 is, 32 does have the ability to be rewritten as 2 raised to a power. In this case, it would actually be 2 to the 5th. And at this point, since I can see that I have two exponentials with the same base, I really could just take the two exponents and say, well, if those two exponentials are equal to each other, then the two powers also have to be equal to each other. So really at this point, I would just set 3x minus 7 equal to 5 and go through the steps to try and solve for x. So I would add 7 first, and then divide by 3 next, and arrive at my final solution of x would equal 4 for this particular equation. Go ahead and move on to example 2 here. This one, notice we have an exponential equation once again, but this time it's not as easy to try and make things match. So if I were to try and rewrite 20 using 3 as a base, 3 definitely would skip over that, because 3 squared is 9, then 3 cubed is 27. It never actually equaled 20, so I can't really rewrite the 20 in terms of 3 being raised to a power. In other words, I can't use the base exponent property. So what I'm going to do is go ahead and just introduce some logarithms on both sides. So I'm going to choose to do the common log, and as long as I take the common log of both sides, everything is okay. At this point, I can take advantage of the power rule, which allows me to move that x in front. So this really could be rewritten as x times log base 10, or the common log of 3. And since the log of 3 really is just a number, right, I could type that into the calculator and it would give me a number. I'm just going to go ahead and divide that number over to the other side. And that would give me my final result here of x would equal whatever log of 20 divided by log of 3 would be. And if we were to maybe go ahead and figure this out and round to maybe like 4 decimal places, it looks like this turns into approximately 1.6224. Now, another option I could have done would have been to actually take a natural log of both sides. So just to show how that would have worked, I could have said the natural log of 3x equals the natural log of 20. Still would have done the same thing, moving the power out front. And then I would have been able to divide by that natural log of 3, just like we did before. And even though I used a different log, I'd actually still get the same value, and if we were to type in natural log of 20 divided by the natural log of 3, we would find that it also equals a 1.6224 approximately. So it kind of comes down to personal preference, which of those two logarithms you prefer. The other thing we also could have done is just converted this from exponential into logarithmic form. In other words, we could have just said x will equal log base 3 of 20. So we also could have done that conversion, but At that point, since we don't have a log base 3 button on our calculator, we would have to use the change of base, and we would ultimately utilize either the common log or the natural log to be able to evaluate it. And notice we would have got either this statement or this statement if we followed through with the change of base formula, because remember the base would go to the bottom. Notice both of those have the base of 3, or the number 3, in the denominator, and then whatever number was inside was on top. So notice with that last example, we had a lot of different possible ways we could have approached it. I actually showed all 3 different ways that we could have actually come up with a solution, so hopefully at least one of them made sense. For this particular one, the first thing we would want to do is try and isolate the exponential. So this 100 that's in front, first thing I would think to do is go ahead and just divide that 100 over. So now I'd end up with e being raised to a power of 0.08t equaling, and if I were to divide those, it looks like that would just equal 25. So I could at this point choose a logarithm to take of both sides, because I can't really rewrite 25 using a base of e. And the one that would make the most sense, because I can take advantage of inverses, is to just take a natural log of both sides. So this one would then allow me to move that exponent out front, or we could think of, well, inverses should cancel each other out, leaving just what's in the exponent. Whereas the right side, there isn't an e as the base, so it would just stay the natural log of 25. So notice I was able to eliminate or get rid of my exponential part. So at this point, I'm going to go ahead and just try and isolate t by dividing by the 0.08. And if we go ahead and type that into our calculator, this one comes out as approximately 40.2359. So notice we had to do a little bit of extra work before we could introduce a logarithm here, in the fact that we had this number in front that I needed to deal with. It wasn't too tough. We were able to just divide it over to the other side, reduce that number, and then once the exponential was by itself, then I could introduce the idea of a logarithm. We could have also done this with a common log, or any other log for that matter, as long as I introduced it to both sides. It just happens to be the natural log canceled the e a lot easier than if I would have chose a different logarithm. Moving on to now example 4. This specific exponential equation is probably one of the toughest formats to try and deal with. So notice we have exponentials on both sides. We've got a base of 4 on the left and a base of 3 on the right. There really is no way to change one of those bases to match the other one. I can't really rewrite 4 in terms of 3, and vice versa. I can't really rewrite 3 using 4 as a power, or 4 as a base. So ultimately what I would do for this one is just introduce a logarithm of some sort. I'm going to go ahead and just choose a natural log. And notice I'm just taking the natural log on both sides of the equation. Why that's going to be helpful is now the power rule allows me to move my exponents out in front as coefficients, so the x's that were in places that I really couldn't do much with now are going to be out in the open. Because there's 2 on this first one, an x and a 3, I will want to make sure that I group them together and say it's really x plus 3 in front of the natural log of 4, and then on the other side I have a negative x multiplying with the natural log of 3. So what I can do is distribute this natural log of 4 through, and that would then give me an x times natural log of 4 plus a 3 times the natural log of 4. And then on the other side I have still the negative x natural log of 3. Now since I'm trying to solve for x, it would hopefully be reasonable to try and get my x's at least on the same side. So I'm going to go ahead and just move the x that was on the left over to the right. So now that gets 3 natural log of 4, which is just a number all by itself. And on the right side I've got a negative x natural log of 3 minus an x natural log of 4. Now why that's nice is because they both have an x, I should be able to actually factor that x out and rewrite this as 3 natural log of 4 being equal to x multiplying with negative natural log of 3 minus natural log of 4. So basically just took the x's that were in front, factored it out, and now what I should be able to do is to isolate x, just divide by that entire parenthesis. So the negative natural log of 3 minus natural log of 4. And as long as I do that on both sides of the equation, it's all good. So this should give us our final result of x would just equal the 3 natural log of 4 being divided by that negative natural log of 3 minus natural log of 4, which we could then type into our calculator to come up with its approximate value. So 3 natural log of 4 divided by a negative natural log of 3 minus a natural log of 4. And this comes out approximately negative 1.6737, it looks like, if I were to round. And one thing you can do is you could check your answer by plugging this back in and just making sure that the left side is the same value as the right side. In this case, it would be relatively close. Because we've rounded, it would be off just slightly, but as long as your number is within a reasonable amount on both sides, you can with confidence go ahead and say, yes, this is a correct response. So that wrapped up the exponential equation examples. Now we'll go ahead and transition into the logarithmic equations. So notice with this one, I only have one single logarithm, and it's being set equal to a single number on the right side. So I can't really take advantage of the property of logarithmic equality. In this case, I would have to actually just convert from this log form into exponential form. So what we could do is just say, well, what's inside x is going to equal, and then whatever the base is raised to whatever's on the other side of the equal sign, which in this case was a negative 2. So notice by just doing that one single conversion, that got the x already by itself. So now at this point, it's really just trying to simplify my result. Because that power was negative, I could drop it to the denominator and make it now a positive power, and 3 squared is a 9, so I really could say that my final answer for this one is x just equals 1/9. Now with logarithms, it's a little bit more important to just double check that our answer is even allowed to be plugged in. Remember, I can't plug in any negatives, and I also can't plug in 0 inside. Since 1/9 is technically positive, it's greater than 0. That doesn't really violate the domain, so this one does seem like it's checking out. Let's go ahead and try out another example here with example 6. Notice this one, now I have multiple logarithms. They do both have the same base. It is a common log, so the first thing that I think makes the most sense to do is go ahead and take advantage of this addition between two logs can turn into multiplication inside of one log. So if I took x and multiplied it with the x plus 3, that would give me x squared plus 3x. So notice all I did was I took the two inside parts and I just multiplied them together to create now a single logarithm. And now I should be able to do a similar step to what we just did on the last example. So this would just be x squared plus 3x being equal to, well, the base of a common log is 10, and then the power on the other side was technically a 1. So this is really just equal to 10. Now because I got a power of 2 involved, it seems like I should probably get 0 on one side. So I'm going to go ahead and just move the 10 over. That way I can have it set equal to 0, and then just try factoring. So in this case, I would want to multiply to the negative 10 and add to a positive 3. Well, that should be a positive 5 and a negative 2 to get me my two possible solutions of x equaling a negative 5 and x equaling a positive 2. Now if we go back to the original, if I were to plug in negative 5, the first logarithm actually would have a negative inside. So that number actually, because it violates the domain, I have to leave off of my answer. Let's go ahead and check with 2. If I plug it into this first one, that would stay positive on the inside. And if I plug it into the second one, 2 plus 3 also stays positive. So this 2 really is still good. So my final answer for this one, even though I got 2 numbers, only one of them actually can be plugged back into the original. So with logarithms, it's always important to take whatever your answer is and just double check if it's allowed to even be plugged into whatever the logarithms were that you started with. Got just a couple more examples for you. This one's, I guess, as you can see, relatively similar to the problem that we had before. In this case, I do have a minus in between them, so that kind of changes things up a little bit, but at least the logarithms have the same base, so I should be able to use the quotient property and make this actually log base 3 of, and then those two things divided. So this would really be 2x minus 1 over an x minus 4. And then still being equal to the 2 that was on the other side. So just like we did before, since I have it as a single logarithm, I should be able to convert it into exponential form, where my base is 3 and my power is going to be 2, so that would be 3 squared on the right side, which I can rewrite this as 2x minus 1 over an x minus 4, being equal to really what 3 squared is, which is 9. Now to get rid of the fraction, I could just multiply both sides by the denominator. That way I don't have to worry about that on the bottom. And this now could be rewritten as 2x minus 1 being equal to, and if I distribute the 9 through, I'd end up with 9x minus 36. So that seems like that's more manageable. I should be able to get x by itself, so I'm going to go ahead and subtract the 2x over to the right and add the 36 the other direction, which would give me now a 35 being equal to 7x. And if I go ahead and divide by the 7, I get my final result of x equaling 5. And just like before we commit to that answer, just make sure that when I plug it into the 2 logarithms I had originally, that they stay positive. In this case, plugging 5 in, I get 2 times 5, then take away 1. That one still works out. And then 5 take away 4, that would still stay positive. So it seems to me like these, or that number, is good in both logarithms. So I'm going to go ahead and commit to that final answer. And if we actually did simplify it, it would have been log base 3 of 9, which has a value of 2, and then minus log base 3 of 1, which any logarithm of 1 is equal to 0. 2 minus 0 does check out and actually equal to 2. So this was a good result based upon the work that we put in. So notice a common thing when it comes to solving logarithmic equations is we usually are going to try and find a way to make it such that there's only one logarithm on each side. So just like the last example, notice here I have this subtraction in between 2 logarithms. They do both have the same base. They're both the natural log, so I can combine them. And because it's subtraction, it would turn into a quotient or division. So it would be 4x plus 6 being divided by x plus 5, and then that would equal still the natural log of x that's on the right. Now what's nice about this scenario is because both sides have the same log, if they truly are equal to each other, then the inside of the logarithm on the left needs to equal the inside of the logarithm on the right. So if I were to basically just eliminate or get rid of the logarithms, that now opens up the ability for me to try and solve for the x that I have. And just like before, I don't really care for that fraction right off the bat, so I'm going to just multiply both sides by x plus 5. That way the denominator cancels, leaving me the 4x plus 6. And here I'll distribute through the x, and that would give me x squared plus 5x. So because I got a power involved, seems like I should try and get 0 on one side. Since the x squared is already positive, I feel like moving everything to the right seems like the most logical thing to do. And if I were to now rewrite this, I would have 0 is equal to the x squared, and then 5x minus 4x is just a 1x, and then minus 6. So just like we had earlier, we'll try and factor this. What multiplies to a negative 6 that will add to a positive 1. That should be a positive 3 and a negative 2, so x plus 3, x minus 2. So my two solutions, it looks like, would be negative 3 and positive 2. And as we've done with every other example, just double check that I can actually plug those into the original equation. This one right here makes it relatively obvious that I can't plug in -3 because I can't have a log of a negative number, so -3 is out. Maybe 2 still will work. 2 times 4 would be 8 plus 6, that's going to stay positive. 2 plus 5, that would stay positive, and plugging in a positive 2 on the right, that also is positive. So it looks like the only real solution I have here is the x equaling positive 2. So once again, even though I got a couple of possible answers, and just by a quick check, can I plug this back into the original, I was able to narrow one of them out, and notice my final answer only was a single number instead of having both numbers that I ended up getting. Anyway, hopefully these examples are helpful in being able to at least build a strategy for solving these types of equations, both exponential and logarithmic. But as always, if you have questions, just reach out and let us know, and we'll do what we can to try and make it make sense. As always, I do appreciate you taking the time watching the video, and we'll catch you guys next time.